We will be starting with the session now. Hello, everyone. Good morning, afternoon, or evening. Dear authors and invited guests, welcome to Technical Session 7C. I am Dimahi Patel, and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic LLP, it is my great pleasure to welcome you to the 10th International Conference on Information and Communication Technology for Intelligent Systems, New York, USA. The 10th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in New York, and the virtual event is being held through Zoom yesterday and today, that is 23rd and 24th May 2025. I hope you will enjoy the knowledgeable and interactive session through the day. In this session, we have 8 presentations. Each presenter will be given 12 minutes for presentation and 3 minutes for question and answers. On 10 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Before we start the session, I would like to introduce you all to the chair for this session. We have with us Dr. Sachin Jain. Dr. Sachin is an assistant professor at Oklahoma State University, United States, with over 19 years of teaching and research experience in computer science and engineering. He has published more than 20 research papers in international journals and conferences. His research interests include wireless sensor networks, artificial intelligence, Internet of Things, blockchain technology, machine learning, pattern recognition, and digital image processing. We welcome you, sir, and I request you to share any few words you may have for the presenters today.
Thank you, Dimahi. Can you hear me?
Yes, sir.
Yeah. Good morning, ladies and gentlemen, estimated participants and distinguished guests. Welcome to a truly momentous occasion, the 10th International Conference on ICT for Intelligent System 2025. As a session chair, I'm delighted to connect with such a vibrant and accomplished gathering of minds representing a rich tapestry of backgrounds and enterprise expertise from every corner of our globe. This conference isn't just an event, it is a dynamic platform where groundbreaking ideas come to life, cutting edge research takes current center stage, and collaborations blossoms. Together, we hold the potential not only to discuss the future of our field, but also to actively shape it. Over the next 2 hours, we'll delve into an extraordinary array of topics that span disciplines and continents, all linked by a shared mission to advance knowledge, drive innovation, and foster transformative changes. So without further ado, let's embark on this journey together. May this session be filled with engaging discussions, enlightening insights, meaningful connection, and exciting new discoveries. Thank you thank you all for being here. Let's make the most of this remarkable opportunity. Thank you very much.
Thank you, sir. We also have with us Dr. Swati Nikam as our session chair. Dr. Swati is an associate professor of the Department of Artificial Intelligence and Data Science Engineering in Pimpri Chinchwad College of Engineering and Research, India. She has total 20 years of teaching experience in computer engineering. Her research areas are cyber physical systems, information security, Internet of Things, and she has published more than 30 research papers in reputed international journals and conferences. Welcome, ma'am, and I request you to share any few words of remark for the presenters.
Hello, good evening, everyone. It's a nice opportunity to be here. And whenever we are connected with such conferences, it's very good to hear, from different researchers who are working on so emerging areas. So hoping to have a great session ahead. And I wish you all the best to all the participants. Thank you so much. Thank you.
Thank you, ma'am. We will be starting with the presentations now. I would like to call Shreya Joshi to present her study on a hybrid machine learning and deep learning approach for robust malware detection.
My screen visible?
Yes, ma'am.
Okay. So shall I start?
Yes, ma'am.
Yeah. So hello everyone. Good afternoon. Myself Shreya Joshi, and I am currently I completed my MTech in cybersecurity from Nema University, Ahmedabad, Gujarat. So firstly, my is hybrid machine learning and deep learning approach for robust malware detection. So these are the myself Shreya Joshi, Professor Vijay Ukani sir, Professor Priyank Thakkar, Druvang Thakkar, and Brudangi Thakkar. So these all are my co-authors. So this is the contents for this research. So abstract, introduction, objective, literature survey, problem definition, proposed approach, my research and analysis, conclusion and references. So firstly, what is the malware? So nowadays malware is a means in every system we are aware that is this is malware. So how to prevent these malware? So in this topic, I introduce a hybrid machine malware detection approach using machine learning and deep learning techniques. And I used I'm using the P headed for the training and analysis. And I use the ML models like KN and SVM, gradient boosting, decision tree, random forest. And for KN and SVM and gradient boosting, I combine these three models and achieved 99.47 training accuracy and 99.21% testing accuracy. And in further analysis, I used deep learning models, CNN and LSTM. With the comparison of these two models, I um, for the deep learning performance after 30 epochs, they gives 99% accuracy, 97% precision, and 98% recall. So these all studies are reducing false positive and false negative for the malware detection. uh, for the next slide, uh, for the malware attacks are becoming more sophisticated and harder to detect nowadays. So traditional detection system often result in high false positive and false negative ratios. So there are growing need to accurate, scalable, and intelligent malware detection methods to. And then I applied machine learning and deep learning approach for pattern recognition of the malware. So I combine ML and DL algorithms for the improved detection performance. So this study proposed the hybrid detection model using ML-DL techniques. So what is the main goal for the research? To enhance malware detection accuracy, reduce error rates, and ensure the scalability. So what are the main object for this study? So the main purpose of this study is to offer a reliable and effective malware detection framework that improve accuracy while addressing the difficulties to by big and complicated such data set and some p files, p header files data set. So the detection performance, I completely focus on the improving detection accuracy, and then optimization, the enhance accuracy and efficiency by optimizing feature selection and model parameters using these algorithms, and scalability and adaptability and real world applications. These are the literature survey. So in five these papers for the past, they used some machine learning techniques, some deep learning technique, and some are performing hybrid learning. So for the literature survey, in the problem definition, what is the problem for this research for this literature survey? So in the existing malware detection methods face reduced accuracy and efficiency, especially with complex and larger data set like PE files. So malware constantly involved through their polymorphism and making some detection for more difficult, and high dimensional features and imbalanced dataset further degrade model performance and lead to biased result. So also lack of and feature selection and affecting some accuracy and scalability. So these limitations highlight the need for the hybrid learning approach, and then I implement this approach and improve the complete performance and the accuracy. So this is the just a second. So this is my proposed approach. So firstly, I combine the KNN for the classify the accuracy and their malware robustness. So second, for the XGBoost, I use the meta learner trait via KNN with the 5k fold uh, 5k fold stacking input on the model. So I combine XGBoost and KNN for first, and then use the hyperparameter tune via grid search CV, and these three combined model gives my best accuracy for the my ML model. So and then I combine CNN and LSTM for the integrated uh, for the pattern detection. So CNN and LSTM mainly focus on their malware behavior and their pattern detection. So firstly I targeted the PE files to classify known and unknown malware with the high precision, and improve performance metrics like accuracy, precision, recall, and lower false positive and false negative. So let's get to implementation part. So these are the data set explanation. So in my data set, there are total 1,38,047 data points, including malware and binning file. So 96,724 are safe samples. 41,323 malware is our malware. So I split into 82 uh, 80% used for training and 20% for testing. So for the and these are balance data, and for the data set and active training and robust evaluation of the detection models. So I applied random forest, SVM, decision tree, KNN, gradient boosting, and LSTM for my project, and these are the results. So this outpost I firstly gives the so my base paper was implement this data set, and for the further analysis I improved this accuracy to 98.56 to 99.56 training accuracy. So I improved this accuracy by implementing hyperparameter tuning. So the what these are key parameters: minimum sample lift and minimum sample split. So and I used the greasersy and cross validation to find optimal parameters and achieve the best accuracy for my for comparing my base paper. And these are the random forest results. So in previous base paper they give 97% accuracy, and in my for I applied hyperparameter tuning for, and I for this 0.99.98% accuracy I give. And these key parameters were carefully adjusted to maximize the accuracy and generalization. I used in this random forest model, I used grid search with cross validation to find optimal configuration. These are my proposed approach. The hybrid model, KNN, SVM, and gradient boosting achieves the highest train accuracy 99.47 with comparing all models. And they performing very good for the malware detection technique, and they a low false positive rate and false negative rate. And these are for the hybrid model. And so in this they 99.10% training and testing accuracy for the 30 using the 30 epochs, and they give strong with performing. They uh, generalize with minimum overfitting. This is my final high model CNN and LSTM approach. So in CNN and LSTM, they detect the uh, my main motto is for comparing the CNN and LTM model.
Excuse me, ma'am.
Yes. Hello.
Gentle reminder
He- Hello.
that you've crossed your 10-minute mark of. This is to remind you. Can you hear me, ma'am?
Yes.
Yes, ma'am. This is to gently remind you that you have crossed your 10-minute mark of presentation.
Okay. Yeah, this is my last slide. This is the conclusion for my project. So I did 99% uh, for the hybrid model, uh, using hybrid model approach. This study provides proof hybrid approach for malware detection techniques, and this is more effective and scalable. Uh, Thank you. Any questions?
Sachin sir, any
Uh,
questions for ma'am?
yeah. How were the false positive and false negative specifically reduced in your approach?
Sorry.
How were the false positive and false negative were reduced in your approach? How you conducted the, like, how to handle the false positive and false negative in your approach?
For this, I am applied this SVM and SVM and gradient boosting for this PE headers file, and I used a hyperparameter tuning for grid search, and using grid search and cross validation for the better decision boundary and lower errors.
And how about the computational cost of your hybrid model? Did you get the question? The computational cost of the hybrid model you proposed.
Uh, I don't understand.
Okay, no worries. Thank you.
Yeah, welcome.
Swati ma'am, any questions?
Yeah, I have one more question, Shreya. Have you done any comparative study with the previous approaches?
Yes, ma'am.
So have you shown that? I mean, so what is your observation?
So, ma'am, in the past paper, so they give 98.56% accuracy, and I used hyperparameter tuning for the better performance. So they give 99.16% accuracy.
Uh, I mean, can you say this is a significant increase in accuracy? Like, now previous approaches are getting till 98.5.
Yeah, ma'am, and I applied this hyperparameter tuning and used the grid search algorithm for the for the best performance.
Okay. Okay, Shreya. Thank you.
Yeah, thank you.
Also, Shreya ma'am, our team had mailed you regarding some updates required for your manuscript. So we kindly request you to give us the final manuscript so that we can proceed with your publication.
Okay, ma'am, sure.
Thank you.
Thank you.
Now, next, I would like to call Balvinder Pal Singh. Sir, please present your paper on AI augmented temperature aware scheduling in HPC using multi level evolutionary algorithm.
Hello, everyone. Can you see me?
Yes, sir.
Yeah, great. So, hi, everyone. If I'm audible well, I think I can start, right?
Yes, sir.
Okay, thanks. So basically, the topic that
Sir,
was,
do you have any presentation that you can share us?
yeah, I'm
PPT?
sharing I'm
Yes,
sharing.
sir.
1 second. Let me know when you see. I think you can see, right? The screen, I'm not sure.
Yes, sir, we can see your
Okay,
presentation.
perfect. I'll start. Okay. Hello everyone. So my topic is basically temperature-aware scheduling in high-performance computing. I think this topic is very hot nowadays, especially when you talk about computing. Myself, Balvinder Singh, and my professor Tangaraju, he and myself actually prepared this topic, and I am a PhD research scholar in IIIT Bangalore, also working in software industry alongside. And the topic that we have selected, as I mentioned, is like mainly temperature-aware scheduling, and we're trying to find an alternate approach to the existing temperature-aware scheduling, and that is what we'll see in the paper. Okay. So moving to the next slide. So the challenge that is posed today, right, is known to everybody, especially because of the overload requirements from AI and ML workloads, especially while adhering to the performance requirements versus the thermal constraints. So the main issue today is the thermal constraint, which is not solved yet. But there are various techniques which exist in the space which we'll discuss. We're coming up with a proposed solution which is a simple solution, but not so straightforward in terms of a, you know in terms of finding out a comparative study. But you can see clearly that we have results in simulation environment, which is a software based approach. So thermal aware OS scheduling. So we believe that the software lies, I mean, the solution of thermal lies in the software rather than the hardware. And specifically, we have stressed on the point where we can, let's say, if I can have a pointer here. So basically, we've stressed on a point where the OS could help reorder the tasks in a thermal way, or in a way where thermal and energy could be optimized. Okay, and the results, as you see, 28%. And by the way, I'll explain the simulation framework in details. So 28% overall performance improvement was observed in the environment. 53% thermal violations were curbed with this approach. 15% decrease in energy consumption, and almost 80% of the jobs were figured out to be running without any degradation. Okay, so it is a two-step process for optimizing, and that will follow. Okay, the first step is towards a genetic algorithm for reordering, and second is for the time slicing. So in this presentation, I would like to give you a thermal landscape, right? Overall, where the market is headed, what's going on very quickly, and how the compute heat is causing an issue. What is the problems or challenges in the existing techniques, and what do we propose, right? TAS is temperature aware scheduling, EAS is the energy aware scheduling, and both are we're trying to go software wise, which is giving us the granularity and more freedom to find a solution. Okay, simulation model has been developed by us, and as I mentioned, it is a two-phased approach. A simulation model is a well-known state-of-the-art techniques used with the various tools. I'll cover that. Phase one, as you see, is making use of the evolutionary algorithms like GA, and we could have used others also, but GA fits us well. Phase two is basically first phase is to find a best schedule, and second phase is to find a rescheduling of remaining jobs. Okay, so that we are under the energy envelope and the temperature envelope of the overall compute engine. And then the results and discussions. So thermal landscape, we have a 400% increase, and this is the data coming from the market. I mean, from the research bodies, for example, CSI, or even the Uptime Institute. So 400% increase in the data center powers since 25, and 31% increase in 2022, 25% increase in 23, and so on. In fact, the rack density, as you see on the right side, the racks, the density is increasing from 9 kilowatts to 130, and projected very high values in 2027. Even the energy requirements are not met. and even temperature requirements are kind of frozen, right? We can't go beyond 120, 115 degrees of the total envelope. So what do we do today, right? The problems today are like it is a heavy kind of, you can say it's oil dunk immersion or undersea data centers being plot, and even the worst case is that the power utilization efficiency, right, which is an uh, index which calculates how efficient we are in terms of energy consumption, energy optimization. So as good as 1.56 on an average, I can see the bottom since last 4 5 years. Okay, this is data from Uptime Institute and colliding with all other surveys as well. So the worst part is that if you put 1 watt of compute, you're supposed to give at the entry 1.56. Okay, so which means that 56% is spent. More majority of the 56% remaining is spent on cooling. Okay, so we're trying to reduce the increase the energy efficiency as well as reduce the cooling cost with this topic, and we came up with this and not only that, I think we're having bigger problem where we'll see the energy consumption are going very high with the data center especially. So now what we do is basically we try to go into a smaller engine, like instead of looking at GPUs and bigger cores to find the problem, we go to a lower core and try to find the real underlying problem. And the underlying problem lies with the hotspots and the compute heat. Okay, so compute heat is the main cause, as we see. On the right side, you see, for example, when you apply load from A to B to C and D, these are the thermal footprints of a particular CPU, 8-core CPU, which shows that the ambient temperature is 28 degrees, and it is going at the case level 60 degrees within few seconds. Okay, and just to highlight this point, that the major problem here is that the power, as and when we grow up into the vertical packaging, 2.5D and 3D packaging, the watt density is very much high. The hotspots are worsening, and various hotspots are created under the layers, underlying layers. Okay, so this is a problem which causes us to detect the temperature detection is a problem. The soft power densities are increasing, rack densities are increasing, and that is the main issue. Okay, what is existing today is all gross techniques. When I say gross, it means that numerous hardware advancements happened in the years, but all these advancements for this is not limited to a particular example, but there are more. But most of them don't know why the heat is generated, right? So we want to control the heat at the source, and that's where the whole research is. And most of the solutions are gross, so which means that they do a system-wide throttling the moment the temperature goes beyond a particular threshold. Okay, so none of them are granular, and we are trying to build a granular per process per core temperature assessment. Okay, one point above about the shrinking reaction time as well. So as and when the node technologies are going down, like from 28 nanometer to about 1.4 nanometer now, the time is reducing, the time window is very much reducing to react. Okay, so all thermal engines should react within 2 to 5 seconds for the latest, let's say 10 nanometer engine, right? And as and when we go closer, it becomes even more difficult to manage, less time to get thermal throttling or thermal management done. Okay, so all these problems are in place. More to add to it, right? I think we also have like problems of hotspot detection. So if we put thermal sensors today, what is happening is we put thermal sensors and you trigger the CPU for throttling the moment the temperature goes beyond. Now you cannot put the sensors in all locations, right? So with 2.5D and 3D technologies, which are like vertical integration, it becomes even more inaccurate, and hence we need to find alternate techniques. Okay, so we feel that the software based solutions would be more granular for tasks constructs. Okay, coming to the need, the OS scheduler will give us more imperative roles to play, especially in the scheduling. So before scheduling, we would kind of make sure that we do a smart job scheduling and know the thermal profile of the job. And this is done by the AI engines, select most optimal job techniques, and then also try to mitigate, find a solution which is very, very easy for tasks. Okay, so what we built, right? This is the proposal, and this is what we have for simulations. So we take a typical CPU array in the simulation. We have a common, a common memory bus, and each of them have a L1, L2 caches and a memory. And what we've delivered is kind of like we built a Gem 5 simulator, which is architectural simulator. We have MC-PAT, which is like a, you can see here, it's an energy modeler, and this is a temperature modeler. So energy, temperature, and CPU architecture. So what we built is a full system here, which could detect the temperature, energy, as well as architectural factors which could cause that kind of energy. Okay, so Gem 5, MEMCPAT, and Hotspot are industry tools for modeling. And this is the result that you see. For example, I took the benchmarks. These are very standard benchmarks from the industry. Whetstone, bit count, and all these are very specific, you can say, benchmarks which are on the simulation or simulator. And we normalize that based on each and every, you can see on the x-axis, you see the benchmark. We ran it for a few seconds without any throttling, and we measured the core temperature, we measured the normalized temperature and power both. So what you can see here is that each benchmark heats the CPU in a different way, and this is showing the model output. And each of them is like heating benchmark, you can say benchmark basic math, large set, small set, matrix, etc. For example, so we take that in an order. What we do is we built a matrix, RB tree, kind of a RB balance tree, in which we put every benchmark in the order of their energy and the temperature profiles, and this is fed to the simulator. Okay, so when you feed to simulator, the first phase that we apply is a GA based temperature aware job scheduling. Here we put a fitness function to reduce the temperature and give a temperature penalty in case it increases to more than temperature 100 degrees, let's say. We also simulate the normalized cooling. So what we do
Excuse me,
is,
sir.
yeah,
Gentle reminder that you've crossed your 10-minute
yeah,
mark.
last few, just two slides, and I will show the results. So
Yes, sir.
here you see, for example, this is the simulation result again for energy and temperature after applying the GA. So on the left side, the tasks were like this, and when on the right side, basically A and B, you see, for example, after applying the GA for the first phase, we found the best schedule. On the left side, you see this is the target temperature after executing. So you see here that it is only 11 jobs out of are already out of the window of 100 degrees, right? If you don't do throttling. Now with GA applied, we brought it back to 4 jobs, only 4 jobs beyond 100 degrees. Okay, you can see on the left side is before GA, this is after GA. Phase 2 basically is trying to get those 4 jobs under control, for example. And this mitigation is either time space mitigation or migration to the other course, right? So with this approach of the phase 1 and phase 2, what we could achieve is basically quite a bit of sequencing hot jobs before or cold job before. So this is generated by GA, and we get these results. For example, DVFS throttles only up to 80% of the tasks are up after optimization. So thermal violations are 26% from 80%, which was originally done. Only 32% size compression, and 73% of jobs were full performance. Okay, even energy dropped by 15%. So we got a good result with this very good result, and within time. Okay, and this is what I want to tell, that with simulation, and also we did a lot of real PC based, real CPU based tests, giving us a good result. Okay, yeah, that's it. Any questions, please? Most welcome.
Sachin, sir, any
Yeah,
question?
thank you, Balvinder. Yeah.
Yes, sir.
So you told that you developed a simulation
Yes, sir.
for this. So could this approach be extended for some real-time or safety critical systems?
Yeah, sir. So what we did is, like, we first of all, okay. So the whole idea was like to figure out that can the scheduling solve the problem, right? So we have other papers, for example, and other chapters that we wrote in our thesis, which are real hardware based environment, and this can be emulated into the hardware straight away. I think there is no you can say 1 to 2%, 1 to 2 seconds of an activity with a very low CPU load. Okay, so this can be extended directly to the CPUs and GPUs. And not only that, I also tried finding one of the CPUs for this job, right? So that you can see one of the cores out of so many cores can do this kind of an algorithm without any penalty. Okay, so kind of this can be definitely extended into the real world.
One more question. Have you proposed any mechanism to handle the sudden thermal emergencies, like if the cooling failure or something like that? Have you
Yeah.
proposed or
Yeah.
in the
So actually, exactly. So this one, right? I think this is actually, if you see, as I told earlier, right, 28 nanometer used to be there in a few years back. Nowadays, we are talking about 1.4 nanometer transistor node technology. So the problem is that this time is squeezing. You can see, like for example, the blue bar is time to read. Let's say you put a thermally just to answer your question. Let's say you put a thermally active job into one of the CPU into the cores. It takes only 2 seconds now in these new CPUs to reach 90 degrees, and another 5 seconds to reach 100 degrees critical, right? So you have only 5 seconds, and this is a real fast thermal breach. And what we are trying to do is within 1 to 2 seconds, we're trying to kick in our engine to find the best schedule which can not heat the, which can without a fan, right? Without fan or cooling, it can reduce the, it can keep bring you back into the thermal engine, right? The thermal envelope. So you take the jobs in such a way. That's what I told. Like for example, there were 11 jobs out in this simulation framework. Out of the 15 jobs that I take, job slices. These are the 15 job slices you can see on the left, and this
okay,
is the data that we took from the simulator. And if you see, 11 jobs were out of the window, right here.
right.
So what, with the algorithm, the first algorithm with the fitness functions, we are able to bring to 4 in this example. It can be definitely worse in other examples, but you can say 4 out of 15 jobs were only out of this 100-degree prediction. Okay, and this is without cooling. So when you bring these 4 jobs back, there is no fan or cooling needed. It can be under the, you can say under the 100-degree mark by just throttling. Okay, so by only software techniques without fan or cooling, within 1.3 to 1.5 seconds, you can bring this back before scheduling.
Have you evaluated the system on heterogeneous networks like
Yeah,
architecture?
that, yeah, right. So heterogeneous, actually, I had tried this on the simulator on the homogeneous, like symmetric network. But for example, we figured out the kind of migration costs, right? So this will kick in when you talk about heterogeneous systems. So we are trying to say that, okay, we can either move these 4 jobs out into the other cores, which are heterogeneous, let's say, for example, and without any performance impact, right? So if there is no penalty, so this can be done definitely. And we have measured the slice reduction will actually, for example, you see, we didn't get enough time, but just if you can give me just 10 more, 15 more seconds, you can see, for example, 2 approaches. Either on heterogeneous, you push this straight away before scheduling into those cores, and you don't see any penalty, no fans, nothing, no cooling, and no penalties. Okay, because you are already done a pre-assessment. But the second approach on the is to time slice reduction. For example, 1.6 slice ratio, 7.4 times slice reduction, 2.14 times slice reduction for these benchmarks. With this reduction, it is going down, as you see, right? So ideally, what I'm saying is either you push these 4 jobs into another heterogeneous, I mean, another CPU which is let's say low energy or a better E-core, or you can do a slice reduction in the same core. So both are possible here.
Okay, okay. Thank you.
Both are possible here. Okay.
Thank you.
Any
Swati
other
ma'am,
questions?
any questions?
Yes, yes, ma'am. So thank you, sir, for the wonderful presentation. I have one question. Like now you have worked on the simulator. So have you tried this with the varying thermal constraints and workload intensities, or maybe any comparative study with the classical heuristics methods or
No,
a
so
single?
so so basically, what I've done is we have used the bottom line as same classical only. For example, I couldn't get enough time, right? But I will just tell you, for example, quickly answering question. So as you see, the classical methods are basically sensor based. Okay, like for
Hmm.
example, today what they do is hardwares have a lot of sensors. Okay, like above the die, before over the die, and all that, right? So
Yes.
basically, what happens is those temperature sensors give you details, but as you see, DTS is the sensor. It reads in this particular example, right? I took it from one of the papers as a reference. So for example, DTS 88.5 degrees it shows, whereas actual hotspot is 92 degrees, right? So the main problem is the DTS cannot be placed in the whole die, right? So classical approaches are actually failing in even detecting the temperature, right? So we have a challenge in, and when you talk about this is only on a die on the top, but if you see the vertical integration, you have multi die above and below, and the heat is trapped inside. Let's say, for example, the hotspot is created under the layer. So it's very difficult for the conventional methods to find out. Actually, there is one more paper which we wrote in ICTIS only, which actually does performance counter based measurements. Okay, so this one is more simulation based, but we have done an alternate of the conventional method, which is performance counter based. So we see the performance counters from the CPUs and various dies and figure out where could be the hotspot, right? That is the best approach that we see is an alternate to the conventional approach. Okay.
Okay. Thank
So
you.
we have two approaches. For example, remove the sensors, have the performance counters replacing the sensors, and second is have the scheduling done in such a way that temperatures are in control within the bracket target temperature.
Okay.
Any
Thank you,
more
sir.
questions, please? Any other questions?
I
That's
have
all from my
another
side.
question.
Good.
Can you hear me?
Yes.
Okay, your simulation basically is supervisor or unsupervised?
No, this simulation is not a kind of I would say it's not a prediction based. It's
Okay.
more of a calculative measurements, right? So this simulator is like a hardware simulated into a software, right? Like kind of so as I mentioned, GEM5 is an architectural CPU architectural simulator. MCPAT is like a is a power engine like a power modeler, and hotspot is like a temperature modeler, right? So this is not a model which is supervised or unsupervised.
Okay.
I would say that I used on top of the data collected based on this simulator, right? A real-time calculation is done on with the estimation, right, in terms of benchmarks.
Okay. Thanks.
Okay, thank you, sir, for your presentation.
Thanks a lot. Good day, everyone.
Now, next, I would like to call Kotsiantin Rishchenko, sir, to present their study on divide and conquer method for constraint programming applied to large-scale production scheduling problems.
Nice to meet you.
Hello, sir.
Yeah, I sent a request to show my screen.
Please try again, sir.
Okay. Can you see my presentation?
Yes, sir.
Okay. Good afternoon, colleagues. I would like to present divide and conquer method for constraint programming applied to large-scale production scheduling problems. And my name is Konstantin Hrishchenko. I'm from Igor Sikorsky Kyiv Polytechnic Institute, Ukraine. So my paper introduced a batch processing method for constraint programming. This approach splits and large-scale input data into smaller subsets, scheduling each subset independently, so rapidly involving the same constraint model and the same solver for these different portions of data. And such approach provided solution time reduction, also memory consumption reduction, in comparison with the scheduling all the data in a single chunk with the help of the same constraint solver from Google or Tools package known as CPSAT solver. What is order scheduling? So in this case, we have different orders defined by graphs of defined by a graph of operations. It's a directed graph, and these operations should be executed by the order defined by this graph, and they should be scheduled into different resources. Also, these operations have different durations, and these durations also dependent onto the resource this operation would be scheduled. So classical constraint programming approach could be defined as a set of constraints. So these constraints could be defined by the equations I presented on the left side of the slide. The main constraint here is no overlap constraint. So on the same resource, no operations cannot overlap. So at the same time, resource could only process a single task or operation. Also, single operation could only be scheduled into a single resource, and operation finish time should be operation start time plus operation duration time, which is dependent on the resource it's scheduled. So classic integer optimization and constraint programming is a very nice approach. So it could found an optimal solutions, but as a problem size grows, processing times goes to the moon. So because it's a NP hard problem, and we need to propose some like scaling method. So this approach could be easily like enhanced and refined to be used in production scale production order scheduling systems. So proposed batch approach splits input data, which is orders, into chunks of the size defined as batch size. It's a parameter we introduce to tune this method. And each subset of these orders is scheduled sequentially. So we schedule first batch of orders, then we memorize values of operation start, operation finish, and resource allocation flag, which defines a resource on which operation allocated. And on the next step, these values would be used as a constant in these constraints we defined previously on a previous slide. So we split like an entire problem into a smaller chunks, and each time we're trying to find values only for some subset of variables. That's why it's reduce the number of variables should be found on in each step. Coming to the results, on the left side you can see a baseline approach. So we schedule all orders in a single chunk with a CPSAT solver. So here is a number of orders. Each order contains a graph of 10 tasks, and we have like 8 resources to be scheduled. On the left part, we can see batch approach. So, for example, for 40 orders, the basic approach couldn't find any solution in a time limit of 5 minutes, and batch approach successfully found the solution in under 1 second, but that comes with the cost. So as we see, MA span, so it's like optimization function we want to minimize is slightly larger, so we lose some like solution quality, but gain possibility to solve large scale problems with this approach. Here you can see a chart of computing time scaling. So as you can see, batch model could be scaled almost linear with the help of this batch parameter. And the basic model is exponential. So for some like production scale orders, it couldn't be applied to solve it in like even in minutes. Also, another point is memory. As you can see, for like for 35 orders, memory consumption was reduced up to 30%, which is nice, especially for cloud environments where a lot of like schedules could be calculated at the same time for different productions, different clients, and like maintaining such scale and inefficient algorithm would be very hard to meet the consumer requirements. In conclusion, I would say that this approach could also be used for other kind of constraint optimization problems. For example, transportation, something like that. Also, for this problem I describe, we could see a 1,000-time-fold acceleration in computation time, also up to 37% memory consumption reduction. So this open possibility to use such like complex method, such almost optimal method to find a solution in real life production scheduling systems. And as a further research, we would like to examine a by-size parameter, how it affects solution optimality, how it affects computation time, and that's it. Thank you for your attention. I would like to have some questions from you.
Sachin sir, any questions?
Yeah. Uh, Very basic question. How the batches are defined or split in your proposed work?
Uh, do you mean what policy I used to split input
Yeah.
data?
Yeah.
So in this case, I used a due date times sorting. So I sorted orders by due date, and that split them into chunks of batch size. So it's like a hybrid between.
So have you defined the size, or
So it's like a
how you
hybrid
decide the
between.
size, like the size of?
Oh, the size is like parameter for my algorithm. So it could be defined like as a hyperparameter. So in when you want to use this approach, you need to define this parameter yourself that better suits your requirements. The larger batch size would be the more optimal solutions you would get, and for smaller batch size would get a faster solution, but you lose an optimality.
Okay. Have you tested this system or the proposed work on industrial data?
In which scale data?
Yeah. Industrial
Uh,
data, on industrial data, like the real time data. I'm to say, like,
it's up to 60 orders. It's mean 600 of operations. It's a larger scale I tested, and we have 1.2 seconds to solve this with the batch size of 5.
okay, can you implement this, or can you integrate this with the real-time scheduling system?
No, it's like not a real time. We schedule all orders in a single request or in a single operation. So it's not real time when orders come one by another. They come into system. So we have all orders from the database and then schedule them, and then we have an entire solution for all orders, all resources.
Okay,
That's it.
thank you so much.
Swati ma'am, any questions?
Yeah, there's one question. Like how you have modeled or resolved those inter-problem dependencies, I mean, as you are using divide and conquer approach. So how do you deal with the interdependency?
Oh, okay. So the main like conflict between these subproblems is no overlap. So in case that operation schedule in a first iteration could not overlap operations in schedule in the second iterations, we used a constants defined on the first operations on the first iteration embedded into this constraint. So the start dates and finish dates for this operation, we no more need to calculate them, but like schedule consistency would be resolved and further scheduled operations would not overlap with them.
Okay. Okay, fine. Thank you.
Thank you, sir.
Thank you.
Now, next, I would like to call V. Machaka, sir, to present the study on fine-tuning protein language models, PMHC's binding prediction case study.
Hello, everybody. I'm going to share. Okay. Give me a second, please. Okay. Okay, hello. My name is Vicente. I'm from Peru. I'm going to explain about how I work in this research about training protein language models for the problem of predicting MAC binding prediction case study. Okay, so these are the overview. We're going to start with the problem. We know that MAC plays a key factor in immune system. For example, in this image, you can see that the MAC is like a shell, as you can see in this image, and this component bind to a protein that is a foreign protein. So it's very important because if the MHC cuts this protein, then MHC can carry to the cell membrane, as you can see here. And it's very important because it's a periodic step in order to activate T cells. So, for example, in many applications like cancer vaccines or drug discovery, it's very important because we need to recognize those foreign proteins. In this context, we are going to develop a method based on deep learning in order to predict this binding. Also, we are going to develop an application in order to show how we can predict. Okay, so the proposal is basically performing two steps. We have a peptide and MHC. Both of them are small proteins. So first of all, we concatenate them. Then we use a pre-trained transformer. In this case, we're using a protein language model. As we know, well, currently there is a lot of language models. So in the other hand, we have protein language models that are very similar to that. So they are also pre-trained with a lot of data, with a lot of proteins data. Then we're fine-tuning that model, adding a long short-term memory block to finally predict the binding between a peptide and the MHC. So how about experiments? So we performed several experiments. For example, we evaluate several lipid parameters configurations in order to fine-tune MSM2 models. These are, well, there is a lot of protein language models. And there is, like, for example, I have them here. For example, there is TAPE. TAPE is a protein language model of 50 million parameters. Bueno, of 92 million parameters. We have also what we evaluate the pro belt with 20 million parameters, and the family of ESM2. We have full scale models in the T6, T12, T33, and T33. For example, the field one has just 8 million parameters, and the biggest has 650 million parameters. We validated all of them. And also, we evaluated several hyperparameter configurations. We compare how about the use of LoRa, distillation, and alleles freezing methodology. Also, we compare all of these protein language models. And finally, we evaluated our best configuration against the state-of-art methods. So, for example, here in this table, I'm showing a comparison between ESN2 models using a freezing layer methodology. I mean, when you fine-tune a protein language model, for example, you can freeze the field layers in order to keep the knowledge, and you just train the last layers. So in this case, I performed that task. As you can see, for example, the small model, the smallest model is performed very well. But there is a problem. For example, in this case, the ESN2 model didn't converge. But when we freeze the field layers, we got to train it. And so on. For example, type is another model. It also didn't convert. But after applying a freezing layer methodology, we can train it successfully. So at the beginning we surprised by these results. So we started evaluating another hyperparameter configuration because it can affect that performance. So in this case, we evaluated these 5 configurations. For example, C1 represents the use of this learning weight with these steps. For example, the problem because some models didn't converge is because they suffer from vanishing gradients. So after reading some in the state of art, we noticed that there is some guidance or some advices in order to choose in order to choose the hyperparameters. For example, we evaluated different learning weights, these, and we evaluated the 1 steps in Adam optimizer. So how we noticed that we were suffering from vanishing gradients. For example, in this case is the ESN2 model, T6, which is the smallest model. And in the left side, we are seeing the gradients in the field layer. So in the y-axis, we see each step, and in the axis, we see the gradients. For example, we can see here that at the beginning, we have gradients with different values. But after the 8th step, the gradients vanishing. So we see a line blue. But if we train that model using another configuration, for example, ICTIS, which has basically a small learning weight, we see how gradients have a normal value in all the training steps. In this plot, we have the same, but it's another model. It's ESM2 T33. But in this case, when we use configuration C3, we see the same problem, the gradients vanishes. But when we use another configuration like C5, the gradients keep well. So we notice that the correct value of hyperparameters depends a lot of the size of the model. In that case, in this table we are showing the training of the ESM2 models, but using several configurations like C3, C4, C5. Also, we include a training using this distillation method, and also LoRa. Finally, we include here the results when we freeze the some layers. And in that comparison, we see that the best model is ESN2 T33 using a distillation method, like in this case. Then we compare the rest of protein language models. For example, we have ESN2, ESN233, the biggest model. We include ProBERT, this is another protein language model, and also we include tape. No? Here also, after this comparison, we noticed that the best model was tape. In this case, until now, we noticed that the best models we have the best performance was tape, and also the ESN233 using a distillation method. And we compare them with state-of-art methods, well, until the last year. For example, we include Anten, this a method based on neural networks. Also, NetMHCPAN is another method based on neural networks. And ATME, MIC, MHCPRED, and MHCFluid. We include all of them. We evaluated them in a data set of a previous work. So we noticed that the proposal works very well in several metrics, despite the precision, because in this metric, well, the best was net MHCPAN. However, in the rest of metrics like tape or like accuracy, recall, or F1 score, the proposal works very well. Also, we include a web application when we have we predict the binding between a peptide and the MIC. For example, in this case, you can include some peptides. Also, you can choose the MIC, and you can submit, and the web application can predict the binding.
Excuse me, sir. Gentle reminder that you've crossed your 10-minute mark.
So
A gentle reminder that you've crossed your 10-minute mark of presentation.
yes. Well, this is our web application where we develop in this research. And finally, well, conclusions. So, in our research, we work a lot. We train several models, several protein language models. At the beginning, we suffer from vanishing gradients. So, in order to mitigate that problem, we use several configurations. And the main conclusion can see that you must use a small learning rate in order to, well, bigger models will need a smaller learning rate. Also, you need to use an optimizer with bias correction. And the learning rate must be used. It's a method that when you, at the beginning, the learning rate must set almost equals to 0. Then it must increase linearly until a certain value, then it must decrease again. Also, we evaluated tape. No, we noticed that tape and ESN2 well the best models, and also they work very well even when we compare them with state-of-art methods. And that's all. We're in future work, we're planning to compare with another protein language models. For example, there is several research that use graph protein language models or use a star method. There are several old techniques. Also, there is new versions of protein language models. We didn't include them because it's very it's very hard to train that models because they implies a high cost. And that's all. Maybe you have any question?
Sachin, sir, any questions for him?
Yes. Thank you, Vincent, for the presentation. I have two questions. What data set were used for training and testing? Have you used the same data set for training and testing, or
Yes.
is it available publicly, accessible publicly, or not? Like,
Yes, well, we use the
can
I
you?
use the data set of HLAB. It's a data set from a method, and this data set is split in training and testing. So we use the training set for training all models, and then we use the testing set in order to compare, no, and that's the result here. The data set is
Can we
public.
deploy?
It's available. The availability is public.
Okay. Can we deploy this in the real-time prediction settings?
Can you repeat the
Can,
question, please?
can you deploy this in real-time prediction settings?
In real-time the
Can you hear me?
prediction? No, currently the web application is no is offline, so we need to download the application using Docker, and we can deploy in a local environment.
Last question. Have you worked on the model like that handles the rare or novel peptides?
Yeah, but it's very difficult to train that models, no, because the cost is very high. So we use paper space, for example, when we have some GPUs. If you notice, we train well, we perform a lot of experiments using not LoRa, using a distillation method. We also perform comparisons with using a freezing diode methodology, for example, in this case. No? We use several configuration methods. So we perform several experiments in order to know what was happening, in order to discover why some models perform better than others. For example, there is something that I didn't mention because in this table here, these are all the protein language models we used. So according to our experiments, tape was one of the best models. No? However, this model just have 92 million parameters compared to this other model, which have 650 million parameters. We believe that tape was better because they use another dataset for the training. All of these models have used several protein datasets for training. So tape, ESN2 use like a very so big data set, which have 60 million parameters. On the other
Okay.
hand, tape use just 30 million parameters. So, but the authors of tape, they filter these samples in order to include just good samples. So we believe that for that reason, tape have a better knowledge about proteins.
Okay. Thank you, Vikram.
I have one question. Can you hear me?
Yes.
Okay, perfect. So in my opinion, I think that maybe if use uncertainty analysis to analyze, for example, the biases provided by models related to data side, it's better than looking maybe to the gradients only, because sometimes it's difficult to follow the comparative analysis between models, since we don't have like the same requirements of data size and
Yeah, yes, of course. I agree. This experiment we are going to include in the future.
yeah, exactly. Yeah. Thanks.
Yes. Yes.
Ma'am, any questions?
No questions from my side. Thank you.
Thank you, sir.
Thank you. Thank you, everybody.
Next, I would like to call Mohammad Iqbal Hussain to present their study on forensic analysis of cryptocurrency transactions, leveraging blockchain for fraud detection and regulatory compliance.
Hello, everyone. Thank you for being here. My name is Mohammad Iqbal Hussain, and I'm presenting our paper titled Forensic Analysis of Cryptocurrency Transactions Leveraging Blockchain for Fraud Detection and Regulatory Compliance. Let's explore how blockchain and forensic tools help us track and fight financial crimes in crypto. All of you know that blockchain has two sides. It improves financial transparency and access, but it's also used for fraud like money laundering and tax evasions. And you may know that new tools like privacy coins, coin mixers, decentralized financing, and NFTs make crimes harder to trace. There are also technical and legal challenges due to pseudonymity and different laws across countries. And we need an integrated system with artificial intelligence tools, better laws, and global cooperation. And from the related literature, we have seen that blockchain is a great for recording transactions that cannot be changed. At the same time, which actually helps to investigation. But coins like Monero hide user identities. And at the same time, we have learned that from the related works, that is, laws are inconsistent between countries and making it easy for criminals to find weak spots. However, artificial intelligence and machine learning can now detect unusual or risky crypto activity. And from those things, we are trying to combining efforts from technology, law, and finance can make investigation stronger. And if you would like to say something about the methodology of our study, actually, we did a detailed review around 174 papers and reports. And from those, we selected around 76 papers that were most useful. We grouped our findings into themes like forensic tools, legal challenges, and new technologies. Actually, this helped us build a clear understanding of in this field. Now, the thematic analysis of blockchain forensics. We analyzed how blockchain is used in forensic accounting. While you can see that tools like chain analysis help privacy coins and mixtures hide transactions. Higher fraud types include Ponzi schemes, ransomware, and fake tokens. However, the smart contract frauds like rug pulls are growing day by day. For the laws and regulations like the FATF traveler rules are helpful but not used everywhere around the world. And at the same time, if we are going through the GDPR, which makes it harder to delete data on blockchain, which causes legal issues actually. Now, if you go through that, the forensic artifact analysis, where we looked at three types of forensic evidence, like on-chain data, off-chain data, and forensics. On the on-chain data, we are saying that public blockchain records used to trace transactions actually. On the other hand, off-chain data, which exchanges records and user information used for only for the identification reasons. On the other hand, wallet forensics explaining that the starting wallets like hot and cold, which are randoms and passwords to trace and recover funds actually. So in this current research trends analysis, we are seeing that artificial intelligence and machine learning are now used to find suspicious crypto patterns in real time. Whereas social media analysis also helps to detect fraud trends. And these tools like GraphSense helps visualization of the real-time transactions and the transaction files. Meanwhile, we are seeing that decentralized financing platforms bring new risks like flash loan attacks, where the legal systems are trying to catch up through rules like MiCA and SEC enforcements. Now, if we would like to say something about the theoretical frameworks in blockchain forensics, we used three theories to guide our analysis. Fraud triangle. Actually, the fraud triangle theories explains why people commit crypto crimes, and due to pressure, opportunity, and excuses, actually. And the another theory we are explaining in our paper, that is routine activity theory, that is based on the crime happens when there is a criminal or a target and no protection is existing in the system. And another theory, that is digital forensic models, which actually helps to investigate, trace, and probe crimes with digital evidence. And a discussion and the synthesis is, we'd like to say that we found good progress, artificial intelligence tools like blockchain tracking and better rules and regulations. But criminals still use privacy coins and mixers to hide their identity, which actually the reason for the lack of global law enforcement and ethical concerns like privacy make things harder, and we need tools that protect privacy while still helping catch bad actors. So this is a proposed model based on our study that we are just proposing, and still we are working on it. That is, our framework has four parts. If you see that artificial intelligence tools, which actually using to detect money laundering and the fraud, and another part is based on the global legal coordination to close law gaps around the world. And another part of our model, our proposed model, that is training programs for the investigators, and then privacy-friendly forensics that follow laws like GDPR, which actually work together. This create a strong, clear system for crypto investigations. Uh, at the conclusion, I would like to say that blockchain is both a tool and a challenge in financial crime. We have made great progress with artificial intelligence, tracking tools, and new rules. But here you have seen that privacy coins, decentralized financing, and lack of global cooperation are still a big problems. So for the future researchers, they can focus on improving the tools, update laws, and focus on smart contract safety and post-quantum security. Thank you. That's all from our presentation, and thank you very much for your attention. We are happy to answer your questions and discuss your thoughts on this important topic.
Sachin sir, any questions for him?
Yeah, thank you, Mohammed, for the presentation. I
Yes.
have two questions. The first one, how does the proposed framework address the
Who's
privacy preserving technologies?
Yes, sir.
How does the proposed framework address privacy preserving technologies? Like privacy preserving, have you worked on that, like how to preserve the privacy? Because you know that the data is very sensitive in this, uh, can be breached, like how do you handling the privacy preventing in this particular proposed work? Did you get the question?
Actually, sir, based on the literature review, uh, we have find out that uh, for the study, we are trying to use the zero knowledge proofs, like probe a transaction is valid without revealing any details about it, like useful in compliance checks. At the same time, we are also looking about the homographic encryption, which actually help us to allow data to be analyzed in encrypted form, where no need to decrypt sensitive information. If we at the same time, we are also going through the differential privacy, which actually adds small noise to data, like hiding individual patterns while keeping group trends visible. And we are also looking for the technology like off-chain storage, which actually stores private information outside the blockchain, reducing exposure on public ledgers. And if we would like to say something about the private blockchains, we would like to say that we are also using the access controls to keep data secure and visible only to authorized parties.
Did you find any technical limitations of the proposed work?
Actually, sir, we are working on our project. So the main limitation is that still we have a lot of real-time data lackings. So when we are very able to get the real-time information more to incorporate in our data in our model, that time we can find out. So right now the limitation is the lack of real-time data.
Okay, thank you, Mohammed. Good work.
Thank you, sir.
Swati ma'am, any questions?
Yeah, I have one question. Thank you, Mohammed, for a wonderful presentation. You mentioned about three theories, I mean, which are being handled. So are you working on all those types? Yeah, yeah.
Yes, but actually, there are three artifacts we are explaining that on-chain
Not this
artifacts.
one, not
Oh,
this one.
which
Next
one?
slide, maybe. Next. Go to next slide. You mentioned about the fraud triangle. Yeah, this one. Previous one.
Yes.
Previous slide. Please go to previous slide. Yeah. Next one. Where you mentioned fraud triangle theory and routine activity theory. So please go
Oh,
on that
yes.
side. Yeah.
Yes, this one.
Uh-huh. So are you working on which one? I mean, and what is your observation like, which helps in real-time problem solving of fraud detection?
Yes, ma'am. So based on the related literature, as we have mentioned that, so for the real-time data activity, so we'd like to say about the fraud triangle theory. Actually, who is helps to develop the profile offenders and identify risk factors. So for this study, if I'd like to compare among the three theories, which one is most perfect for this study and which one is more real-time basis, I would like to say that that is fraud triangle theory. And this theory is really helping us to know about the pressure, opportunity, and the rationalization of different types of threats and frauds in financial industries. So yes, I would say that fraud triangle theory.
Okay. Thank you, Mohammed. Thank you.
Thank you very much, ma'am.
Thank you for your presentation.
Thank you. Have a good day.
Now, next, I would like to call Alexander Rachkin, sir, to present their study on multi-state self-semi-supervised learning.
Okay, I will demonstrate my screen. I'll share my screen. Can you see it?
Yes, sir.
Oh, okay, can I start?
Yes, sir.
Thank you. Good day, everyone. My name is Alexander, and today I will present work entitled Multi-Stage Self-Semi-Supervised Learning, abbreviated comprising LPS. In the next 10 minutes, I will outline the motivation, walk through the algorithmic core, including the precise loss functions, and highlight the empirical results that establish a new state of art. So first we have a problem statement. We leverage hybrid supervised learning to perform classification across two datasets. Let X be our full set of samples. We split it into a small labeled set at the first endpoints and a much larger unlabeled set XU. Assume each label Y takes values in range 0.1, so we have two classes. Our goal is to obtain predicted labels for all X under the condition that some data points are labeled while others are not. We assume that the class distribution may be imbalanced and that the raw data may be poorly separable by standard labeling methods. We have very small label data amount. Labeling large-scale datasets is slow and expensive, so limits downstream performance. Pure self-supervised models excel in representation learning but can underperform on fine-grained classification. Semi-supervised approaches that rely on pseudo-labels face confirmation bias loops. So our goal is simply combine the high-level representation of power of a self-SL with the label efficiency of semi-SL while mitigating their individual weaknesses. So main idea of this new approach is to combine self-supervised and semi-supervised learning on the same dataset to improve the classification accuracy on real noisy data. The approach is based on two methods. Unsupervised learning on unlabeled data with contrastive loss nets SimCLR and semi-supervised learning use the extended Poisson-Seidel learning method. We will go about these methods which we are using in the next slides. So please don't worry about that. In the first preprocessing step, we use contrastive SimCLR approach to classify the data. So what is SimCLR? It's a simple framework for contrastive learning of visual representations. It's a self-supervised learning method designed to produce high-quality image embeddings without manual annotation. The basic idea is to train a neural network to produce representations in which two different embeddings of the same image are made as similar as possible, while representations of different images are made as different as possible. Then we have a second step, where we use new Poisson-Seidel semi-supervised learning approach that allows using a very small number of initial labels while achieving the best accuracy. So our core idea to solve a problem where we have less than, let's say, 1% of labeled data in really large data sets. We have some core components of our algorithms. First is pre-tuning. Algorithm 1 is contrastive learning. So we have inputs labeled plus unlabeled datasets X and Y, batch size N, temperature, Poisson weight parameter, number of epochs. Then per epochs we do next steps. We sample mixed batch of labeled and unlabeled examples, which we use pseudo labels. Augment each example twice to get two views. Encode and project pass each view through an encoder and small MLP model. Then we normalizing it to get the projections. Then we define positive pairs, which we are using the same pseudo labels for, and negatives. Then we compute in ways and simply computing contrastive loss, updating our encoder and projector via backpropagation on average. In output, we have a pre-trained encoder that produces representations with tight intra-class clusters and well-separated inter-class gaps, ready for downstream label propagation. Then we have algorithm 2, which called Poisson-Seidel. It's a summary of this fine-tuning algorithm. Let's get over with it. So the goal is to spread labels from a small set over the data graph by solving a discrete Poisson equation with Gauss-Seidel updates. So we have inputs such as initial labels, graph built via KNN methods. We don't care about method in our approach, so please don't look after it too much. And number iterations. We pre-compute in Laplacian, we pre-compute in source terms, initialization, where U is matrix or class potential, and do the iteration steps. So why it works? Each update solves one row of the Poisson system equations. LU equals FM. Using the newest neighbor values, giving fast conversions and robust label spreading when labels are scarce. Neuronet SimCLR. This tiny SimCLR model does two big things. So it takes any image encoder, in example ResNet, adds a lightweight projection head on top and spits out a normalized feature vector that is ready for our contrastive learning. So why does it matter? So separation of concerns by isolating the projection head, the network team's representations tuned for contrastive objective without polluting the core encoder. Second reason is better transfer. After pre-training, we throwing away any projection head and keeping only encoders. So downstream tasks benefit from clean, semantically rich features, and that's simplicity and performance too. So with just a couple of extra layers and normalization step, we can unlock state-of-art self-supervised learning that rivals fully with many supervised approaches. So next slides are showing results of our new approach, novel approach on different types of datasets. First four datasets called two moons. It's purely synthetic datasets which serves academic purpose. And as we can see, it's our approach are showing really good result on distinctive two classes. Then we have more difficult examples, such as embedded moons and torch moons, datasets which are divided into two classes with over 90% classification rate. Then we have real dataset for medical domain of knowledge, which is called cardiovascular disease dataset, which offers accuracy 73% and over 70%. It's like 70, it's really rounded down. But as we can see, our dataset is really chaotic and really noisy. And on the output, we have two really distinctive classes. There goes the comparison with existing methods, which shows that our approach is scored best out of all existing datasets. Also, we have some cases on missed datasets where we put in label data in 1% or less on amount of several sounds total data points, and as we can see, it turns out really well. Also, it's worth to mention that a best result on GitHub is about 90%. So we got 6 and 5% of improvement overall. And that's a second case where we 0.01%. So very, very label, very unlabeled data set, very scarce labels, and which shows over 94% of results. So a novel hybrid approach to data classification is proposed that utilize both self-supervised and semi-supervised learning methods, such as contrastive loss, Poisson Seidel, and the main idea to first perform a preliminary classification without labels, thereby enhancing the differences between classes, and then to use a minimal amount of labeled data for the final classification. The proposed method demonstrates improved accuracy compared to existing approaches, as confirmed by experiments on both synthetic data and real medical data, such as cardiovascular dataset, which was given in slides. The obtained results, such as 82 and 73%, are best reported to date in the Kaggle database. And from this database, we have to compare GitHub results, which are slightly better, not slightly, but significantly, 6%, or it's a significantly data better for 1% labeled data. So that concludes, that wraps up my presentation.
Any questions for him, sir?
Yeah, thank you, Alexander, for the presentation. Uh, have you discussed about handling the noise in your proposed work, like the
Can you?
training noise, the feature noise? Can you hear me?
I can hear you, but can you repeat the question, please? 1 second.
Uh, yeah, the question is how the proposed work addresses the label noise and the feature noise.
Yes, it has some features, and what exactly we can work out with any features we like.
have you worked on the noise in the data set? Like there may be like have you worked
I
on
got
any
your questions.
you
We are
got me
doing
my question?
pre-tuning with contrastive learning. We sorry for interrupting you. I would like to answer. It seems I got your question. I will try to answer it comprehensively. So we have really noisy data set. What we should do with it? We do pre-tuning step. We have, which is what is hybrid proposal? We are training neural networks, and on the second steps, we are not using any neural networks, but we are strictly label propagating from existing labels, clear labels, to whole data set points. So our contrastive learning, which is pre-tuning, it's for you. It's what used for removing some noise, and also we can add some features, but I haven't looked deep down into that. There are many ways to remove the features. I choose which are best available to us right now, like some products, and
Okay.
I
Have you tested
incorporated.
this on?
Yes, yes,
Yeah, go ahead.
yes.
Go ahead, please.
Okay, and I incorporated this into whole like schema of working out a large data set, which has like some very, very massive amount of unlabeled data points.
Okay, thank you.
Ma'am, any questions for him?
Yeah, I have one question. What are the challenges you faced in this?
This work is challenged by itself because it isn't discussed by anyone right now, or if it's discussed, it's like in really simple matters. No one has done right now combined methods of semi-supervised and self-supervised learning to incorporate this with some like enhancements on mathematical side, because nowadays I search for some Kaggle problems. I'm really looking up to solve some medical problems in my academic path right now. So I'm looking for similar tasks, and similar tasks are not working out to many exceptions, and they are not relatable to me. So I'm trying to operate with just basic information, and my uh, my work is having too hard time to being verified. As you can see, I need all data sets, all kinds of data sets. I need synthetic data sets. I need real world data sets for verification of my schema, of my novel approach, for it to be novel first, and for it to be working second, and third, for it to be for it to show the best results on the market.
Okay, have you shortlisted any problem to apply your work?
Yes. I will show you presentation one more time. Specifically, I worked on cardiovascular diseases, so predicting if a person hardly it's predicting if person needs an operation or if it doesn't, judging on large data sets. Because what's the problem, what's the issue now? Doctors can handle to label too much data, so we can automate the process. And to automate this process, I show and develop my approach and give it as a project to clinic right now. It's process around that are building.
Okay, okay, thank you.
Okay, thank you, sir.
Thank you.
Now, next, I would like to call Amir Aib to present their study on multitask learning strategy for surrogate hydrological modeling.
Okay, hello everyone. Let's first start introduce myself. My name is Amir Ayab. I'm a PhD student from University of Bolzano, located basically in the northeastern of Italy. So my research background focuses about Earth observation with a particular focus about climate science. And today I want to talk a bit about advanced learning strategy to predict hydrological parameters across spatiotemporal scale, basically by including multitask learning. So our work is structured in different sections. I want first start providing a brief overview about water balance system. Then talk a bit about physical-based model limitation. And we select the IDG catchments as a good example for study area because this area is characterized by high variation of elevation. And for data exploration, I want to talk a bit about the impacts of climate change on hydrological parameters. And we have also a section talking about our proposal approach. And for the results and discussion, we provide a comparative analysis using different deep learning model architecture across different scale. And then for conclusion, I want to highlight the most significant outcomes obtained in this work. So basically, the estimation of hydrological components like soil moisture or maybe stream flow or others like runoff is critical. Why? Because the most of the model used in this area is physical based and requires a lot of parameters for calibration. It means like the model in this case is costs, and especially when we work about large scale. So the other points is about the climate time series data is not uniform and not stationary, and this is also impacts on the quality of the results and make deep learning model have difficulty to optimize the hyperparameters across large scale. So this table basically provides a comparative analysis of different physical-based model. We can focus about some of criteria like the cost, application, and limitation. For example, taking the case of a VIC model, this model is able to simulate several parameters, and however, if you want just to apply this model for 1 year of prediction over a superficie of 10 kilometers square, this model can take 60 hours. So you can think maybe if we go to large scale, so this model it become quite impossible, especially if we use, for example, a sample computer characteristics. And for example, for the case of WFlow as advantage, it can be used for high resolution. It's better than the VIC because it takes half of time for training, and only the problem is the required a lot of parameters for calibration. For example, in this case, 42 parameters, and the problem is the most of these parameters is coming from different sources, and it's hard to obtain, especially if we work about high resolution, like 10 meters of resolution. And the last model, high achievement model, is faster, but the problem of this model, it can be applied only for some cases like extreme events, so also limited for special resolution. So based on the state of the art, as alternative solution to predict hydrological parameters, we can use gas-based model. Gas-based model. So basically, this model is twin of physical-based and deep learning model. So we can ask a question, for example, here, why we need to use physical-based model since we are trying to avoid this model. So basically, physical-based model in this architecture is just applied for small scale, just only trying use this model to prepare a ground truth data for our deep learnings, and also the physical-based model can help us optimize the distribution geophysical parameters and get the best calibration parameters. So then the deep learning will be applied to learn the dependencies between the ground truth data, which is hydrological parameters, and we have climate data and calibration parameters, which is the geophysical information about the landscape. And once the model will be defined, then we can apply it for large scale. So our study area, so we select IDG catchments, which is located in the northeastern of Italy and the southern part of the Alps region. So this area is characterized by high variation of elevation from 20 meters to 3,610, which provide very good scenario of all Alps region. So basically, and for our data, so basically we are using as input data climate parameters such as precipitation, temperature, and potential evapotranspiration. And for ground truth data, we are using soil moisture. So this figure provides some statistical description analysis about data distribution across the region from 2018 to 2022. So as a result, we can see like both precipitation and potential evapotranspiration have a high interannual variability, while temperature and soil moisture are stationary and stable during the years. So to go ahead with processing analysis, we start first to understand the impacts of this input data on ground truth. So using the feature selection like very importance. So from this figure, we can understand that potential of actual evapotranspiration have a very high importance to predict soil moisture, and also from the cumulative distribution plot, we can see like the curves, like highlighted by the green colors, it's mostly similar to the yellow one comparing to the other. So let's go ahead with this parameter to understand more how the potential axial evapotranspiration can impact on soil moisture prediction. So basically this figure shows the variability differences between the potential axial evapotranspiration and soil moisture. We are using here like red rectangles to show that the potential axial evapotranspiration overestimates soil moisture, and green shapes to show that this parameter underestimates. So from this result, we can understand that during the spring and summer season, that mostly potential axial evapotranspiration impacts so much on soil moisture. It means like both parameters, they have like very high differences in terms of variability. So our model pipeline is based on integrated like some layers to deep learning model, starting by making a pre-processing. So first of all, we apply a 3D encoder, apply on normalized climate variable, to better like represent our data as a single 3D feature, and also to make the pre-processing step more easier. Then the second step is by applying special polling. So basically in this step, we define techniques to better like view the special pixels as one single pixel, able to show like the time scale of our data. And then the next step is basically help us to reduce the time scale from multiple years to one single year in order to understand the patterns of climate data. And doing that, we can use like a simple method like autoencoder function to detect seasonality. Once we have this information about different season, it becomes like more easier to resample our data in different seasonal data sets. And making that help the deep learning model share the hyperparameters learning and provide very good results. And the last step basically is calibration. In this step, we use geophysical parameters to minimize the biases provided by multitask surrogate deep learning model. So here are the results of using 3D autoencoder. In the first row, we show like first we have the result of encoded climate data. So basically we use precipitation, temperature, and potential evapotranspiration. So to evaluate.
Excuse me, sir.
Yes.
Gentle reminder that you've crossed your 10-minute mark.
Okay, that's good. So basically, this figure like shows the performance of the encoder model. Here we look like how the model using the decoder can reconstruct data with high accuracy, and you can see the result basically is ranging from 0.81 to 0.91. So basically, in this figure, so we show the result of special polling. So basically, we propose a technique is based on the weighted average pollings. So weighted average, by using uncertainty, we can get like shape mapped values, and using these values, we can apply a weighted average to our special data in a single. So this figure basically shows the results of spatial polling, and we can see from the density plot that by applying weighted average is better than using the mean polling. So we can see here from the score that's basically the symmetric divergence here in this case is equal to 0.41, comparing to when using normal like polling is 0.50. So in this figure, we show the result of frequency encoder in like in this case, we are applying basically the autoencoder on the same scale, so to reduce from multiple years to one single year. So from the results, we can see that the model performed very well. Okay, in this slide, we show the results of seasonality detection. Basically, we set up our autoencoder function to detect just for the season in order to provide the physical explanation in our domain. And basically, this is the different season that we obtain by using autoencoder applied on the fusion climate data. So here the results basically of using different deep learning model to predict soil moisture. So during the dry period, the first case is by using like simple architecture of deep learning model. Basically, you are using like LSTM, convolutional LSTM, bidirectional LSTM. Here it's after improvement by including the multitask learning. So we can just follow the shape. Basically, we can see that the bias is decreased after using our like approach, and the model is work very well to predict data with all the models. In this case, so basically for the waste period, so we have a small improvement before we show just like the climate data have very impact on soil moisture only in the dry period. So in this case, we can see like the model also like we can only use the simple architecture of like LSTM. We don't need like to include learning basically. So here the result of predicting soil moisture using LSTM during different seasons. We can see basically the improvement of the model during different seasons. So the red colors show the results of multitask learning using LSTM, and the blue colors is using like simple architecture of LSTM. And from the table, you can see the R2R basically. So there is improvement in all like seasons, and we can see like significant improvement in spring season. So you can see also like here the density plot, how it look after like using multitask learning, and here
Excuse
like
me, sir.
the results. Yeah, I am just on the last slide.
Yes,
Okay,
sir.
last slide. Okay, thanks. So here basically is the time series. So we pick up different, like 3 different applications from our region, so with different elevation, just to show how the model can work very well in mountainous region. So we can see in all cases like the green colors like plots overlap on the black one. That means like the LSTM multitask learning perform very well compared to LSTM. At conclusion, we have like basically by using a sample architecture of deep learning model, bidirectional LSTM outperform like LSTM and convolutional LSTM, achieving R square like up to 0.91, especially in wait period. However, like this model can provide biases in the dry period, especially when the evapotranspiration over its main wait. And also from like our work, we have like by using two-level encoder, also like we can simplify the climate pattern and also make it easier to detect seasonality, like by using a simple models like autoencoder, autocorrelation, sorry. And as the last point, like we can just point out like including multitask learning can improve the accuracy of surrogate deep learning model around 10%. Yeah, across like our scale. Yeah, thanks for your attention. If you have any question.
Sachin, sir, any questions?
Yeah. What are the sources of the climate and soil moisture data set and how large they were?
So basically, climate data is obtained from EOPS, 1 kilometers of resolution. So is available in different like websites, for example, in from NASA or NWA, for example. And we are using for our case like 5 years of data. So basically, we use the first 3 years like to train the model, and the last 2 years like to test it.
Okay. Can this approach be scaled on a global level or like global soil moisture prediction? Is it possible, like, or is it restricted to a localized or specific regions only?
Yeah, we can use it also like for global soil moisture. Like in our case, the challenge is like it's important for our case because we are using high resolution claims data. But if we go, for example, for global soil moisture, basically the resolution like decrease, and the model can work very well. Yeah.
Okay, thank you.
Never mind.
Swati ma'am, any questions?
No questions from my side. Thank you.
Okay, thanks.
Thank you, sir.
Okay, thank you so much.
Now, next, I would like to call V. Machaka sir to present their study on Neo-Argos tools, a flowchart pipeline tool for neoantigen detection from single nucleotide variants.
Hello again. Okay, I'm going to share my screen.
Sir, I would request you to please be concise with the presentation due to the time constraint we have.
Okay, thank you. Okay, I'm going to start. Now I'm going to explain about Neo-Algos tools, which is a flowchart pipeline tool for neoantigen detection from single nucleotide variants. Okay. So as we know, cancer is one of the one of the main health problems in the world. For that reason, cancer immunotherapy arises. For example, we have the development of personalized cancer vaccines, the development of immune checkpoints inhibitors, and adaptive T-cell therapies. In this work, we focus on neoantigen detection, which is a key step in the development of personalized cancer vaccines. In order to understand that, we need to explain the difference between single nucleotide variants and structural variants. The difference is very simple. Single nucleotide variants refers to mutations in a small group of peptides. Meanwhile, the structural variation refers to mutations in a big group. Several cancer types are related to structural variants. Also, how is the process of the development of personalized cancer vaccines? First of all, we need to take samples from normal cells and tumor cells. Then we need to sequence the DNA, in this case. The sequence process is just getting this information. For example, here we can see that there is some mutations that are related to cancer. Then we need to perform neoantigen detections, in this case. And this is the in silico part where I refer to a big process, a big computationally process. And well, the research is focused in this step. Then the vaccine is developed. We add some adjuvants in order to make the vaccine stronger. Finally, the vaccine is injected to the patient. With the objective is that antigen presenting cells recognize them. That also the T cells can be activated, and also it can be multiplied and destroy the cancer cells. So how about neoantigen detection? It's just one part in this big process. But neoantigen detection is also a very complex process. For example, here we are taking some samples from from a normal cell and a tumor cell. Then we need to, when we sequence that samples, then we need to check the quality. Here we have several tools, for example, FaceQC and Thermomatics. Then we need to align the sequences in order to know, no, to know the variants. Also here we have another tools. Then we need to improve this alignment. Then we need to detect the variants. We can use Strelka, but there is another group of tools we can use in each step. Also, we need to filter all these variants. Then we need to annotate these variants. And in this step, we get thousands of neoantigens. And finally, we need to prioritize the neoantigens. Here we use also the research where I presented before, where we need to predict the binding between neoantigens and the MHC. So in each step, we have several tools. It's very complex. Normally, researchers use they connect to a server. They code scripts. It's difficult to log errors. It's difficult to choose one tool. Also, the pipeline depends a lot of the input data. For example, if we are going to use single nucleotide variants, there is a sample pipeline. If we want to use structural variants, the pipeline will change. So it's so complicated. No, it implies a lot of effort. For that reason, we propose. Well, we are proposing the development of a graphical user interface in order to define pipelines for neoantigen detection. In this first version, we are focused only on single nucleotide variants. For example, here is the proposal. We developed that using React Flow and Flask for Python for the backend. And here in the left side, you can see we have several tools. The user can choose the most appropriate tool according to the task. And in this zone, the user can plot the flow. Also, for example, according to each tool, for example, in this case, each tool have its own parameters configuration. So, for example, in this case, star is an alignment tool, so the user can set up some parameters. Also, the user can see the input and the output of each tool. Then here, for example, here is an example of a pipeline. As we can see, we are using some samples. We are checking the quality, the alignment. Here we are detecting variants. It's known as variant calling. We are using mutex. We are filtering the variants, and we are using ANOVA for variant annotation. And finally, we are using these tools for peptide binding with the MHC, like Flowey and Net MHC PAM. This is an example. The user can run it, and the user can see the execution of each step and can see the input and the output from each tool. Also, this is another example. In this case, we are using BWA after alignment tool. We are using Strelka for variant calling. And this is maybe the most the advantage of the proposal, because first of all, we see a graphical interface. We can see the whole pipeline. We can see how is the process, and we can see the input of and output of each step. Currently this tool is available on GitHub. You can download it using Docker. Well, as I said before, neoantigen detection is a complex process. It implies a lot of effort. So for that reason, we propose Neo-Algos tools, which simplify this process. It offers a graphical user interface. It's easy to use. It's easy to run, and also easy to manage. it reduces the complexity a lot. Well, in future work, we are planning to improve the scalability limitations. For example, normally this kind of pipelines require a computer with a high capacity. For example, in our experiments, we were using 50 gigabytes of memory RAM, so it has some limitations. Maybe we are planning to use some cloud services, and also we are going to include, we are going to improve the log of errors and warnings. Also, well, in this first version, this pipeline is focused for single nucleotide variants, but we plan to include structural variations and gene fusions, which have very, well, it's known that they are very related to several cancer types.
Excuse me, gentle reminder to conclude your presentation.
Thank you. Yeah, that's all. That's all. Maybe there is some questions.
Sachin sir, any questions for him?
Yeah, one question. Uh, like what kind of user is it designed for? Like for bioinformatician or for biologists or for clinicians?
It is for bioinformatics
Is it
users. They are the normal users that
bioinformatics?
develop
Yeah. So
pipelines.
do they require do they require any coding knowledge for this using this?
Yeah, currently bioinformatics they code in command lines. They use Unix instructions. They also use Python code, out language. So I know, as I know, they struggle in this process. So our main objective is to make it easier, to get into this field.
Okay. So does the proposed system has any limitations?
Yeah. For example, we need a computer with high capacity because currently the bioinformatics use a server. They connect through command line to a server. No,
Other than that,
in this version we can run it locally, but you need a computer with high capacity.
no. Do you find any limitations of the proposed system?
Yeah. Now we are considering only single nucleotide variants, but neoantigen detection depends a lot of these variants. The most research I refer to include structural variants or gene fusions. So we are planning to include them in the future.
Okay, thank you.
Swati ma'am, any questions?
Yeah, I have one question. Like how this work would handle conflicting data? The
Conflicting
proposed.
data.
Yeah, these
Uh,
tools.
yeah, well, I understand that maybe there can be some errors in the process of each tool. Do you refer to that the kind of conflicts, or what conflict of data do you refer? Excuse me. Well,
Hello.
yeah. For
Have you
example,
come across any conflicting data in your work?
yeah. Okay. No. Well,
Then how
currently,
this tool?
okay. Well, in this field version, we didn't include analyzing any conflict of data. We focus only in the capacity, on the functionality that the user can choose some tools and can draw a pipeline, and the user can see all the execution of each step. But currently, when manage conflict of data, or maybe a good manage of logging errors, something like that.
Okay. Okay, thank you.
Okay, thank you, sir, for your presentation.
Thank you.
Now all the presentations are done. I sincerely thank our authors for their excellent presentation and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. We, on behalf of the whole team, thank you for the support during this 10th version and all the previous 9 versions of the conference. All the presenters would be getting their digital certificates through email within 2 working days. The publication will be live within 6 to 7 months, hence, kindly cooperate with the team of ICTIS 2025. I would like to thank our session chair, Dr. Sachin R. Jain, for chairing the session. I'm sharing a token of appreciation on behalf of Team ICTIS and Global Knowledge Research Foundation partners. Sir, I would request you to share any closing remark you may have for the presenters.
Yes. Dear participants and guests, it has been truly inspiring to witness the depth of expertise and the diversity of the perspectives shared during the session. Uh, a special acknowledgement must go to the incredible team behind this conference, including the organizers, sponsors, and the dedicated team of volunteers who are the true backbone of this event. Your tireless effort, often behind the scene, have played an essential role in making this session and the entire conference a meaningful and memorable success. Once again, thank you all for your enthusiasm and contributions. All the best.
Thank you, sir. I would also like to thank Professor Swati Nikam for her valuable presence as our session chair. Swati ma'am, I request you to please share any remark you may have for the presenters, and I'm sharing a token of appreciation on behalf of the team.
Thank you, ma'am. And thank you to all the participants for the wonderful presentation. I mean, it was really wonderful to hear from different participants on different topic, and that too in so depth. They have studied, they have implemented, they have designed. So it was a really wonderful experience. So I thank all the participants, and I thank GR team, ICTS team also. Thank you so much. And I wish uh, a good research. I mean, please continue your research and benefit everybody. Thank you.
Thank you, ma'am. I kindly request everyone to please turn on their camera for a snapshot of this virtual conference. All right, thank you, everyone. Have a great day ahead. Thank you.